Hey there, and welcome to this explainer. If you're a newer developer just kicking off your coding journey, I'm absolutely thrilled you're here. Think of me as your senior mentor today. We're going to take that late-night stomach-dropping panic you probably feel when using version control, and we're going to replace it with real, lasting understanding. We're breaking Git down from the absolute ground up so you can finally stop guessing and start thinking in graphs and pointers.
Because look, we've all been there, right? Mass copying commands from Stack Overflow, just crossing your fingers and praying you don't somehow make it worse. It's 11 p.m., you just tried to pull some code and suddenly, boom, there are merge conflicts everywhere. You're sitting there absolutely terrified you just nuked your team's entire project. You use Git every single day, commit, push, pull, and it works like magic. Until it doesn't. And here's an uncomfortable truth about our industry. A lot of experienced developers don't actually understand Git either. They've just memorized a bunch of commands. But for us, that stops right now.
Okay, so here's our game plan for today. We're going to explore the Git family tree, discover why branches are really just sticky notes, map out the 3 layers of Git, navigate the whole danger zone of changing history, and finally, we'll see how the reflog is your absolute ultimate safety net. All right, let's dive right into section 1. The Git family tree, and how to understand the core database.
Okay, so first things first, I need you to forget everything you think you know. At its heart, Git is fundamentally a database, and the core building block of that database is the commit. Now, here's what's actually super fascinating about how Git defines a commit. It's not just a list of the lines of code you changed, not at all. It is a complete, full-blown snapshot, like a photograph, of your entire project exactly as it looked at that one specific millisecond. And every single commit contains 3 totally crucial things: a pointer to that complete snapshot of your files, some metadata, like who made it in your commit message, and, this is key, a pointer backward to its parent commit. Now, because every commit points backward to the one right before it, it creates this long chain going all the way back to your very first commit. In computer science, this structure is called a DAG, or a Directed Acyclic Graph. But look, don't let the fancy terminology intimidate you. Just think of it as a family tree. The directed part just means the relationships only go one way. Children point backward to their parents, always. Parents never know about their future children. And the acyclic part, that just means there are no loops. I mean, nobody can be their own grandparent, right? So at the end of the day, Git is literally just a giant family tree of snapshots. Moving right along to section 2, branches are just sticky notes. Let's demystify how we actually move around this graph. So when developers try to navigate this massive family tree of commits, they almost always assume a branch is this huge, heavy, complex thing, like it's a completely separate copy of the entire code base. That is 100% false. A branch is literally just a sticky note. Honestly, it's just a tiny text file containing one single piece of information, the unique hash of a commit. That's it. It's just a little label slapped onto a commit in your graph. When you create a new branch, it happens instantly, because Git isn't copying hundreds of files. It's literally just writing out a new sticky note. Even the main branch? Yeah, that's just a sticky note we've all kind of collectively agreed to treat as our primary timeline.
Okay, so we've got commits and we've got branches pointing at those commits. But how does Git actually know where you are in this giant tree? Well, meet head. Head is Git's internal pointer that tracks your current location. Usually, head points to a branch, say your current feature branch, which then points down to a commit. But what happens if you check out a specific commit hash directly instead of a branch name? You enter what's known as a detached head state. I know, it sounds like something from a horror movie, but it just means head is pointing directly at a commit floating out in space, without a branch in between. I actually knew a developer who once checked out an old commit to test something, found a bug, fixed it, committed the fix, and then swapped back to main. Because they weren't on a branch, they didn't have a sticky note, that fix was instantly orphaned and eventually got swept away by Git's garbage collection. 2 whole hours of work, just gone. The takeaway here, always use a sticky note.
All right, let's look at section 3, the 3 layers of Git. Where is your code actually living? Before we get into fixing any mistakes, you absolutely have to understand the physical layers of Git. This is absolutely crucial. Git operates using 3 completely distinct areas. First off, you have your working directory. These are the actual, tangible files you're looking at right now in your code editor. Second, there's the staging area, which is sometimes called the index. Think of this as the waiting room. It's where you meticulously prepare exactly what's going to go into your very next snapshot. And third, we have the repository. This is the permanent database of commits we were just talking about. So let's walk through how this creates your standard day-to-day workflow.
Step 1. You edit some files in your working directory. Git notices, sure, but it honestly doesn't care yet. Step 2. You run git add. This takes those specific changes and moves them into the staging area, our waiting room. Step 3. You run git commit. Git takes everything sitting in that waiting room and permanently locks it in as a brand new snapshot in the repository. Grasping how your code physically travels through these 3 layers is your golden ticket to undoing mistakes without losing anything. In fact, let me share a quick story. I had a junior dev who totally froze up during this terrifying merge conflict. I told them, look at the 3 layers. The conflict was actually just sitting right there in layer 1, the working directory. So I had them fix the overlapping code right in their editor, run git add to push those fixed files into the staging area, waiting room, and then finally run git commit to safely lock the fix into the repository. By just visualizing those layers, what felt like a scary project-ending conflict just turned into a simple 3-step checklist.
Which naturally brings us to Section 4, Time Travel and Changing History. Brace yourselves, because we are officially entering the danger zone.
Pay super close attention here, my apprentice. Let's imagine you just completely broke the login page. You've got a few options. Checkout is totally safe. You use it to time travel backwards and just safely look at the working login page from yesterday without breaking anything. Reset, on the other hand, is risky. You use reset to aggressively rewind time, actually deleting your broken commits from the timeline. But then there's revert, which takes a totally different approach. Instead of erasing history, revert creates a brand new commit that does the exact mathematical opposite of your mistake. Revert is your absolutely safe undo button, especially when you've already shared that broken code with the rest of your team.
Let's actually zoom in on reset for a second, because this right here is where developers accidentally delete days of hard work. Reset has 3 different modes, and they interact directly with those 3 layers we just learned about. A soft reset moves your branch pointer back, but it leaves your staging area and your working directory completely alone. It's actually really great if you just want to combine a few commits together. A mixed reset takes it a step further. It clears out your staging area, but still keeps your working directory safe and sound. But a hard reset? Total danger zone. A hard reset moves the branch, completely clears the staging area, and violently overwrites your working directory. Any uncommitted work you had sitting on your disk is instantly vaporized, gone forever. So seriously, only use a hard reset if you are 100% sure you want to abandon everything you're currently doing.
Okay, so what happens when you're done building your feature and you want to integrate it back into the main timeline? Well, you've basically got 2 choices, merge or rebase. Merging, which you see on the left, is the messy truth. It creates a brand new commit that actually has 2 parents, showing exactly when and where those 2 parallel lines of work mash together. Rebasing, on the right side, is the clean story. Rebase looks at your feature commits, calculates the changes, and essentially replays them one by one on top of the new main branch. But wait, remember our core database rule from earlier? If you change a commit's parent, you change its hash completely. Git literally has to create entirely new commits. Because of this, if you ever rebase commits that a colleague has already pulled down, and then you force push your newly rewritten history, oh boy, your whole team is going to experience this massive explosion of conflicts and duplicate changes. So write this down. Never, ever rebase shared history. And finally, Section 5, reflog saves the day. Let me introduce you to your absolute ultimate safety net. Let's set the scene here. You ignored my mentor advice. You went ahead and ran a hard reset trying to escape a messy conflict, or maybe you just completely botched a rebase. Suddenly, all your commits are gone. You run a log, and your graph is just empty. Your stomach absolutely drops. Your project seems utterly lost forever. Okay, take a deep breath. I promise you're going to be okay. Git almost never truly deletes anything immediately. It usually just hides things. Enter the reflog. The reflog is this incredible hidden local history log that basically acts like a treasure map. It literally records everywhere your head pointer has been recently. Every single checkout, every single commit, every single reset. It's all there. So those lost commits from your terrible reset, they are actually still sitting perfectly fine in the database, and the reflog has the exact hash pointing right to them. So here is your exact rescue mission to save the project. Step 1, open your terminal and run git reflog. You're going to see a list of all your recent movements. Step 2, just scan down that list until you spot the hash of the commit from right before you made your disastrous mistake. Step 3, remember our golden rule that branches are just sticky notes? Just run a simple command to create a brand new branch pointing directly to that recovered hash. And boom, your work is completely recovered, sitting safely on a brand new branch like nothing ever happened. Now, there is one tiny little catch you do need to keep in mind.
The reflog isn't infinite. Entries for reachable commits usually expire after about 90 days, and for unreachable orphaned commits, it's closer to 30 days. So while Git absolutely has your back, you can't wait 3 months to realize you've lost something important. But if disaster just struck 5 minutes ago, you are perfectly, 100% fine.
So, my apprentice, we've arrived at our final question. The next time a command breaks your repository, are you going to blindly copy code from the internet and just cross your fingers? Or will you take a breath, visualize the 3 layers, and actually think in graphs and pointers? Because I promise you, once you truly see Git for the simple database it really is, you'll never fear it again. Thank you so much for joining me on this explainer, and I'll catch you in the next one.